Okay, how do we do such updates in practice in an efficient way? So this is a simple pseudocode for implementing TD Lambda efficiently in a continuous way. So here, this is very similar to TD learning as we've seen before, to one-step TD learning. But now we also keep, by the way, this is a tabular, TD Lambda in the tabular case. Later on I'll show you how to extend this to the approximation case. But the idea is about the same. So if we'll understand how to do it in a tabular case, it will be a simple extension to the approximation case. So what we do is now, instead, on top of the TD0 that we've seen previously, we now also store an eligibility vector. So some eligibility value that is some value between 0 and 1 that represents the eligibility. There is one value for each state in our state space, right? So this is only applicable in the tabular setting. We'll see the changes that we need to do for the approximation case in a second. So at each time step, we'll keep an eligibility score for each one of our states in the state space. Okay, so we initialize it to 0. And each time we visit a state, we'll update the eligibility to be very high, and it will diminish over time. Okay, after we visit a state, each time we visit a state, we increase the eligibility, and it will be exponentially decaying over time. Okay, so as long as we perform learning at each time step, we update the eligibility to visit, the eligibility to learn from the last action. We'll update that value for the state that we just visited at time step t, st, right? And we'll update this value based on the weight values that we defined in the previous slides. Now, in many implementations, if you look at those online, you might, or in other publications, this value here might be replaced, the 1 minus lambda, might be replaced with 1 instead of 1 minus lambda. And this is not a problem, as this is a constant that can be seen as part of the learning rate, alpha, later on. It can be accumulated in the alpha. But the weights won't sum to 1 in those cases. But again, this is usually fine. And you'll see that in many implementations. Okay, next we update all states based on their current eligibility, right? And this is done in vector notation. So V is the state values for all of the states. And we do this based on the current TD error multiplied by the eligibility vector for the current update. Okay, so of course we will do this update to the state st, the one that we just saw, with this with 1 minus lambda eligibility. But we'll also do the same for the state that we saw 2 steps ago with some diminishing eligibility, and for one that we saw 3 steps ago, and so on. Right? We'll update all of the previous states based on their eligibility. Right? And so here we're actually updating all of the states, right? This V is a vector over all of the states in our state space, but not all of the states has a non-zero eligibility, right? Only those states that we've seen previously in the current episode. Okay, next we're going to decay the eligibility for all of the states, right? Including the state that we just saw, because once we move to the next time step, the eligibility for the current step will diminish exponentially by multiplying it by lambda. Okay, so as we just saw, the first time we visit a specific state, st, we update its eligibility to be 1 minus lambda, based on the equation that we saw previously. And the state value for this state, for ST, that we visited at this at the current time step, will continue to be updated at each future step with diminishing eligibility, as we just saw, right? So the eligibility will decay with lambda over time. After we visit state Sn at time step n, for instance, we update S0, the state that we saw initially at time step 0, with, according to the TD learning rule, but by multiplying it by the eligibility, a very, the eligibility will be decayed by a power of n at this point, but with we'll update it with some very small eligibility.
Here will be value of S naught, right, in this equation? Vs.
The Vs, right, it should be V of S naught, and here as well, V of S naught. You're right. Good catch.